Hello everyone, welcome to this lecture on dynamics of the lithosphere. The topic of today is elasticity and regional isostasy. This is part 1. Previously in dynamics of the lithosphere, you've learned about the structure of the Earth. So at the very center is an inner core which is solid. It is shelled by a liquid outer core, and going towards the surface is a massive layer which is the Earth's mantle, and the external shell or solid shell is the lithosphere. So the lithosphere contains the crust and a part of the rigid mantle, and the crust can be either oceanic and continental. The lithosphere is able to deform and to localize deformation. What we've also been studying in the previous lecture is isostasy. And to study isostasy, basically the aim was to understand how thick or how dense is the crust in regions of varying topography. And we were assuming that the crust, like this giant duck, is floating on top of a fluid mantle. So that's an approximation that works to a certain extent, but does not always work. And we ended up the lecture with this example of a seamount, which is loading the oceanic lithosphere. So you see a volcanic edifice here, which locally thickens the crust, and the moho is being deflected, but not only locally, it's being deflected also away from the load. So local isostasy cannot explain this. And to explain this observation, we need to take into account rigidity of the plate. So the models we learned in local isostasy were the Airy and the Pratt model. And now we want to move to regional isostasy, and we need to consider what's called the elastic flexure. So what you would obtain without taking into account resistance is a local model. If you thicken the crust locally, then the mantle below is deflected without resistance. But if you load a plate which is elastic, which has a certain thickness and strength, it will bend, and this bending will have a non-local effect. So that would be elastic flexure. This is well described in the case of cements, as I have shown you in the previous slide. Typically, we can describe the cement as a load. There is a 4 dip, so you see that basically the moho, for example, will be deflected here. It will be deepest right below the load, but as a result, there will also be a bulge. So a bit further away from the load, there will be a positive deflection, which will be recorded. So to explain this, we need to move to a regional model. Moreover, the same model of regional isostasy will not be only applicable to cements, but it will also be applicable to the case of subductions. So a subduction zone you can imagine as a plate, so that would be the lower plate, which is sinking into the mantle. But this plate has a resistance, so when it sinks into the mantle, it deforms, and part of the plate is indeed elastic. Therefore, there will be a typical morphology of the seafloor close to subduction zone. There will be, of course, the zone of maximum deflection is where the plate is the deepest, but away from this region where the subduction driving force is applied, there will be a deformation leading to the formation of an outer rise, which is a positive deflection away from the trench. This is a non-local effect that can also be explained with regional isostasy. That's a very nice 3D view of cement loading coupled to a subduction zone. So in that case, you have the cement here, and you see that it is loading the plate, leading to a fore bulge away from the plate. And there is a progressive deflection associated to the load. And the same goes with the subduction zone. So the subduction is deflecting the plate downward and leading to a massive fore bulge here. So the elastic effect of a subduction zone and caused by the loading of the plate can be interacting. Another type of elastic flexure is that associated to magmatic intrusions. So here is the case of a laccolith. So a laccolith is a magma injection which is made into a layered sequence of rock, and you see a magma here injected is inducing deformation of the overlying crust. An example of this, a most famous example of this, are in the Henry Mountains in Utah. So you see a section of a laccolith here, and the field picture, basically the fat layer here is crystallized magma, which is shielded by sediments that have been deformed. This we can also model with a fairly simple configuration. So to model this kind of process, we will consider an injection point, a rigid base here, and a plate which is elastic. So the pressure induced by the injection will deform the overlying plate, which represents the sediment. So to study all these processes, the keywords are in fact flexure and elasticity. And just to illustrate again the process from a more intuitive side maybe, here is the guy jumping on the board. If the board is weak or thin, then the board will deflect a lot. If the same person is jumping on a strong board, or here a thicker board, then the deflection will be minimized. So the spatial distribution of deflection and amplitude of deflections also depend on the plate strength and the plate thickness. That is in contrast with what we learned in the previous lecture on local isostasy, because there we were neglecting any strength effect. So to move forward and become able to study flexure and apply it to lithosphere deformation, we first need to study a bit the basics of elasticity. Therefore, this lecture will provide you some basic elements regarding strain, stress, and constitutive relationships. So we first start with strain, and I guess this would just refresh your mind about the concept of strain. Let's consider a bar which has an initial length Li. If it's being stretched, then it will reach a final length Lf. So the final length is Li plus delta L. We can define, for example, here an elongation. So that's a uniaxial measure of strain along this x-axis. This is the final length minus the initial length divided by the initial length here, delta L over Li. The question is, what is the unit of the elongation strain here? This is unit length, meter, these two, and these two. So meters divided by meters gives no unit. So strain has no unit. In general, we want to construct or we want to describe the strain in 3 dimensions. And for this, we will use a measure of the strain, which is here the infinitesimal strain tensor. It is a second rank tensor. So the expression of the infinitesimal strain tensor is epsilon ij is equal 1/2 of dui dxj plus duj dxi. So u is the displacement vector and x are the coordinates. So that's how u can be spelled out. It's one vector that contains a x, a y, and a z component. So the displacement is, again, it's unit meter. So let's make an example of some expression of components. So we have epsilon ij. This is the formulation with indices or index notations. And as I told you before, it's a tensor, so it can be written as a matrix. Here's the infinitesimal strain tensor written as a matrix. You see that in 3 dimensions it will have 9 components. So you have the diagonal components, which are strains in the direction normal to each of the faces, epsilon xx, yy, and zz, and these are the shear strains. These are symmetric. Then let's express some of the components. We want to express epsilon xx. So this is the normal strain along the x direction. So to express epsilon xx, we will start from this expression here, the general expression, and we will use or replace the indices by x. So epsilon ij will become epsilon xx, and this will be 1/2 of dui is equal to x, dxj is equal to x, and same applies to that side. So it becomes dux dx plus dux dx. So that's 1/2 of 2 dux dx. So it makes simply dux dx. Now if you want to express the shear component, epsilon xy, we will substitute I by x and j by y. And this will become 1/2 of dux dy plus dui dx. We cannot simplify it further than this. So that's for the infinitesimal strain tensor. Now we need to discuss about stress. And what is stress? Let's use some intuition again. So the stress is a force which is exerted through a surface. So the unit of stress is Pascal. It is a force through a surface. It means that Pascal is simply Newton per meter square. And now let's consider that a person that weighs 70 kilo is either walking with high heels or with snowshoes. The person that weighs 70 kilo exerts a force of approximately 700 newtons, so 70 times 10. And the high heel section is very small, 1 centimeter square, while the snowshoe section is 1000 centimeter square. The stress is the force divided by the area. So let's compute the stress exerted by this person with high heels, and we compute the stress exerted by the same person, but this time wearing a snowshoe. So you can compute that stress here is 7 megapascal, just below the high heel. On the other hand, the stress exerted by the snowshoe is 7 kilopascal. So there is a factor 1000 difference between these two cases. And in one case, if the person would be walking with high heels on the snow, it would completely sink inside the snow, while with the snowshoes you can remain at the surface of it. So what does it mean? It means that the deformation of the snow below is not controlled by the force which is exerted, because in both cases the person exerts 700 newtons, but it is controlled by the stress that the person exerts on the snow. So a person with the same weight will cause different stress regarding the type of shoes, and this will control whether the snow will, how the snow will deform below the person. So the stress here drives deformation. It's the stress that matters, and it's not only when you walk, it's also everywhere. So stress drives deformation, it matters. It's tightly coupled to, for example, reactions in rocks and materials, and that's an example of a recent call that was made to study stress-induced corrosion. So corrosion in power plants is governed by stress too. So one has to be very careful with this type of process, because this may affect nuclear power plants. So what is stress? In general, the stress can also be expressed as a second rank tensor. So let's spell out the components. If we have the strain tensor, which has this matrix appearance, we can also express the stress tensor with the similar components. Now, in most cases, both the strain and stress tensor are symmetric. So we can simplify from 9 components, we can simplify to 6 independent components in both cases. So you should notice that here you have xz, zx, xy, yx, yz, zy, and in this case, if you assume symmetry, both these components are equal to each other. Another useful thing to do is to use Voigt notation to express the strain tensor and the stress tensor as vectors. So that's a vector notation. You see the 6 independent components written in a single column here. Rho transpose is a column. The same applies to the stress. So that's a vector notation. You will see why it's useful afterwards. And now we want to relate the stress to the strain. You know that strain has no unit, while stress has unit Pascal. There should exist an object here that will relate these two quantities. So D here will be a tensor that contains material parameters which are to be evaluated by rock deformation experiments. It is a 4th rank tensor. It means it has explicitly 4 indices instead of 2. So what are the units of the components of D? That's a fairly simple question. Here you have no unit, here you have Pascal, so the components of D in the case, in this case here, D is unit Pascal. And this is how bad things get when you express this tensor. Now you see that we use strain in vector notation and stress in vector notation. So strain is here, stress is there, and in between there is this big matrix that basically has 6 columns and 6 rows, because we consider 6 components of the strain and stress tensor. So the good news is that if everything looked a bit complicated and dense right before, things can be simplified using symmetry again, or material symmetry. So in the case of isotropic elasticity, which is what we will use during the whole course, the matrix reduces to a simple expression. So in isotropic elasticity, we will need only two coefficients to express this matrix. These two coefficients would be, in our case, the Young's modulus E and the Poisson ratio nu. And you see a lot of zeros have appeared here. So a lot of these coefficients from the very dense matrix here are simply vanishing under the assumption of isotropic elasticity. So E, the Young modulus, and nu, the Poisson ratio. So the Young modulus can be measured from experiment. So if a rock deformation experiment is made, the rock is being strained and the stress is being probed or measured. And in the initial stages of deformation, elasticity matters. The Young's modulus is the slope of the stress-strain curve. So this is unit stress, Pascal. This is no unit strain. So the slope here has unit Pascal. This is the order of magnitude of Young's modulus for rocks. It's about 10 to 100 gigapascal. So that's a big number. The second coefficient of interest is the Poisson ratio. And the Poisson ratio is a ratio of actual strains. So you have to imagine if you compress this volume here and it deforms into this other volume, the dotted line, you will cause actual strains, and the ratio between epsilon x or epsilon xx and epsilon y is actually the Poisson ratio. So what's the unit of the Poisson ratio? The Poisson ratio is the ratio of two strains which both have no unit, so the Poisson ratio has no unit. The magnitude of Poisson ratio, it's basically between 0.2 and 0.5 for geomaterials. So a few words about volume change, because the Poisson ratio is actually quantifying the volume change in a way. How during elastic deformation the material can change the volume, so that, for example, if you have a pressure wave or if you have thermal contraction, how do we measure this, or how do we express the volume change? It is the divergence of the displacement. So you have nabla dot u here. It can be written as epsilon kk. So let's maybe express this a little bit more explicitly. In 3 dimensions, nabla dot u is the sum of the diagonal component of the strain tensor. So it's epsilon xx plus epsilon yy plus epsilon zz. So here, if you write it epsilon kk, it means k is an index that runs from x to z, and then there's a summation implied. So you will have xx plus yy plus zz. It is also the trace of the strain tensor, sorry. So if you take the stress tensor written as a matrix here, you can take the trace. So the trace is the sum of the diagonal elements, epsilon xx plus epsilon yy plus epsilon zz. Similar measure exists for the stress, and this would be the pressure, for example. So what is the pressure? The pressure is also related to the trace of the stress tensor. In fact, here it is the negative mean trace. So we will take the diagonal elements of the stress tensor, we will multiply by 1/3 to get the mean, and multiply by -1. This is a convention in most in our field. So it can be written as sigma kk if you use the index notation and Einstein summation rule, 1/3 and -1. This is the pressure. So pressure as unit Pascal. So as a summary, the material deformation can be expressed as a strain tensor. The stress is a force which is exerted over an area, and what matters for deformation is actually the stress rather than the force. The stress tensor can be expressed as a tensor, and the stress and strain, they are related via a tensor of rho-g coefficients. And the good news is that for our case of linear isotropic elasticity, only 2 coefficients will be needed to describe the rheology of the material. So that's very important, because knowing, with this basic knowledge, we will be able to move forward and really now study the flexure of plates. So in the next lecture, we will use the knowledge from stress and strain to try to describe the deformation of plates, and in particular to apply it to lithosphere deformation. Thanks for your attention.